Welcome to the video lecture for Chapter 13, Solutions and Their Properties. This chapter's content largely builds off of Chapter 11, so make sure that you've got a good understanding on that material before diving into this content. As you will have learned in Chem 1211 or an equivalent course, a solution is any homogeneous mixture, one that has a consistent composition throughout. The components of a solution are the solvent and one or more solutes. The solvent is the major component of such a mixture, and solutes are any minor components, any of those other than the solvent. In principle, a solution can consist of any phase of matter dissolved into any other phase, but the types you will have previously focused on, and this remains true for this class as well, are mainly solids, liquids, or gases dissolved in liquids. Let's look at what happens on a molecular level when two or more substances combine together to form a solution. Before the two substances are mixed together, there will be intermolecular forces holding together the molecules in the solute, and the same is true for the molecules in the solvent. In order for the molecules of the solute and the solvent to mix together homogeneously, the particles in both need to be dispersed to some extent. That involves overcoming some of the intermolecular forces present initially in the original substances. Much like what goes on when a solid melts or a liquid vaporizes, overcoming these intermolecular forces requires the input of energy. Therefore, dispersing both the solvent and solute molecules are endothermic processes. However, when the two substances mix together, new intermolecular forces are formed between solute and solvent molecules. These new, favorable intermolecular interactions involve a release of energy, much in the same way that freezing a liquid or condensing a gas releases energy as the intermolecular forces increase in strength in both of these examples. Hence, this part of the mixing process is exothermic. To summarize, forming a solution involves overcoming solvent-solvent interactions and solute-solute interactions, both of which are endothermic processes. And energy is also released when new solvent-solute interactions are formed, so that part is an exothermic process. If we plot this on an energy diagram, we can see how these processes interact. The total enthalpy change for the formation of a solution is determined by the relative strength of each of these three steps. If the solvent-solute interactions are stronger than the combined solute-solute and solvent-solvent interactions, the total enthalpy change for forming the solution will be negative, or exothermic. Energy is given off. Likewise, if the solvent-solute interactions are not as strong as the combined solute-solute and solvent-solvent interactions, the total enthalpy change of forming the solution will be positive, or endothermic. Let's consider two real-world examples, both involving the dissolution of an ionic solid in water with an initial temperature of 25 degrees Celsius. On the left, we have calcium chloride dissolving in water, which is an exothermic process. Hence, the temperature rises. On the right, the salt ammonium nitrate causes the water temperature to drop when it dissolves. This is an endothermic solution formation process. On a molecular level, the way an ionic solid like those two dissolves in water is depicted here. If sodium chloride, for instance, dissolves in water, the sodium cations and chloride anions undergo a process called hydration, where they become surrounded by water molecules. Since water is a polar molecule, where the oxygen atoms are partially negatively charged and the hydrogen atoms are partially positively charged, the oxygen atoms of the water molecules are attracted to the positively charged sodium cations. Likewise, the hydrogen atoms of the water molecules are attracted to the negatively charged chloride ions. As a result, each ion dissolved in the solution is surrounded by water molecules as shown in the diagram. There are other thermodynamic considerations when solutions form, namely those to do with entropy. You may or may not have come across the notion of entropy last semester, so either as a reminder or for the first time, the simplest way to think of entropy is as a measure of the randomness or disorder of a system. If we form a solution by dissolving a solid, which has very ordered arrangements of atoms, molecules or ions, into a liquid, there's going to be an increase in entropy. We're starting with two pure substances, and especially in the case of the solid, the particles are organized in a very ordered fashion. After the solid dissolves, we have a randomized dispersion of different solute and solvent particles, so almost any process that forms a solution by dissolving a solid into a liquid will involve an increase in entropy. If we mix two liquids together, the process of forming a solution here also leads, in most cases, to an increase in entropy. Even though the particles in liquids aren't as well ordered as they are in a solid, a solution formed from two different liquids still results in a randomized dispersion of multiple different types of particles, and hence an increase in disorder. Okay, but why bother caring about entropy? It turns out that we need to know both the entropy and enthalpy changes for forming a solution to predict whether two substances can actually mix together to form a solution in the first place. At the top of this slide, we have the equation that tells us whether a solution-forming process will occur spontaneously or not. Spontaneity, in the context of thermodynamics, refers to whether a process or a reaction can occur on its own without any external input of energy. If we plug in the enthalpy change for a solution, delta H, and subtract the product of the temperature in Kelvin and the entropy change, delta S, we get what's called the Gibbs free energy change, which is delta G. If this delta G value is positive, it means that a solution will not form spontaneously. In other words, the two substances cannot mix together to form a homogeneous solution. If the delta G value is negative, on the other hand, we do have a solution that can form spontaneously, and the substances are capable of mixing together to form a homogeneous mixture. Hence, if we know the enthalpy and entropy changes associated with a solution forming, like we see in this table for the formation of aqueous solutions of some common ionic compounds, we can predict whether they can dissolve in water. Now that we know some more about how solutions form, let's talk about how we can measure their concentration. One way you learn to do this in the first semester of general chemistry is in terms of molarity, the ratio of the number of moles of solute in a solution to the volume, in liters, of the solution that contains that amount of the solute. Molarity is an important concentration measurement for many purposes, but it's not the only one we'll need as we go through this chapter's remaining content. Other measures of concentration are mole fraction, the number of moles of one component of a solution, divided by the total number of moles, the sum of the number of moles of solvent and all the solutes. Another is mass percentage, which is a measure of concentration that pretty much tells you what it is just from the name, what percentage in mass or weight terms of a solution is made up of one of its components. So the mass of the component of interest divided by the total mass of the solution, including the mass of the solutes and solvent, times 100 to convert from a decimal to a percentage. Last and not least, we have molality. This is a bit of a problematic name. Not only does it sound a lot like molarity, which is a different way of measuring concentration, but it's also abbreviated as lowercase m compared to molarity's uppercase m. That notwithstanding, the molality of a solution is the number of moles of solute divided by the mass of the solvent in kilograms. Note that this is not the mass of the solution in total, but only the mass of the solvent itself. For an aqueous solution, for instance, that would be only the mass of the water. Here's an example of a problem that often confuses people before they've seen it worked out, converting from one concentration unit to another. Let's consider seawater, which has a density of 1.025 grams per milliliter and has a concentration of 3.50% by mass of sodium chloride. How can we use this information to find its molarity? The key to starting a problem like this is to assume that we have a certain amount of the solution. Concentration is an intensive property, so choosing an arbitrary starting amount won't affect the final answer. The concentration information we already have is the mass percentage, 3.50%, so the easiest option is to assume that we have 100 grams of the solution. Why? Because of the way percentages work. If the solution is 3.50% sodium chloride by mass, that means that 100.00 grams of the solution should contain 3.50 grams of sodium chloride, so no complicated conversion is needed to find that information. Now, if we're trying to find the molarity, we need to know two things: the number of moles of sodium chloride and the volume of the solution in liters. We can convert the 100 grams of seawater to volume by using the density of the solution, first to milliliters and then to liters. The number of moles of the solute, sodium chloride, is just that mass of NaCl divided by its molar mass. Taking the two numbers from the previous slide and plugging them into the formula for molarity, we end up with 0.614 molar, or 0.614 moles of sodium chloride per liter of seawater. Let's look at another example. The molality of a solution, in this case, one containing 0.385 grams of cholesterol dissolved in 40.0 grams of chloroform, a liquid solvent. Molality is moles of solute divided by kilograms of solvent, so we first need to find the number of moles of cholesterol. This is given by the mass of cholesterol divided by its molar mass, which gives us 0.000997 moles. We already know the solvent mass in grams, so converting that to kilograms is just a matter of dividing it by 1,000, giving us 0.0400 kilograms. Dividing the two numbers according to the definition of molality, we get 0.0249 molal, or 0.0249 moles of cholesterol per kilogram of chloroform. Okay, but why do we even need different ways to measure solute concentration in solutions? This chart gives a quick rundown of the advantages and disadvantages of certain concentration units. Besides the reasons listed here, we'll see a few formulas later on that express certain solution properties in terms of concentration, and the particular equations use different concentration units.